Hi there. Today's video will be looking at steady state heat transfer through a cylindrical pipe. So first of all, we'll be looking at conduction. So when you have a cylindrical pipe, so the pipe is in this form. So this is our inner layer of the pipe and then this is our outer layer of the pipe. So we can redraw the pipe as something like this. Right? So when to look at the heat of conduction, we know that heat of conduction is through two solid medium, right? So the heat transferred from this inside of the pipe to the outside of the pipe. That's what we'll be looking at for now. So if this is the center of the pipe, from this point to this point is our radius. So let's say R1, inner radius. And then from this point to the outer part is R2, our outside radius. Now, if the inner portion is at a temperature of T1 and this will be at a temperature of T2, we are looking at the heat transfer. So when we have a fluid flowing through the pipe, the fluid is going to flow through the pipe in this manner, which is horizontal manner. And then the heat transfer will be in the vertical form. So let's say it will be in the radial direction, right? Because if there is a hot fluid flowing through this, heat will be transferred from this portion to the inner wall of the pipe, and then it will be transferred from the inner wall to the outer before from the outside to the environment. So the heat of conduction will be by radiation. That will be, sorry, it will be in the radial form, right? So our heat of conduction is KO not KO being equal to KA. When I negate this K, it means that my dt here is actually the smaller one minus the higher one over dx. So when I bring negative here, it means that my dt here is actually the cold minus the hot, right? But then if I neglect the negative, it means that it's the hot rather minus the cold. Our heat transfer here will be in the radial direction. Previously, we were looking at the one in the x direction, right? Where the thickness was in the x direction. And now because the transfer will be in the radial direction, we are going to get minus Ka dt over, so our dx now becomes dr because it's in the radial direction. And then because we are now looking at a cylindrical pipe, so our area here wouldn't be length times breadth. It will now be 2 pi rl. So 2 pi r is the curved surface area, right? And then the length will elongate it to a certain length. So this becomes our area. So Q becomes negative K multiplying 2 pi rl and then dt on dr. Now mostly when there is a hot fluid flowing through this, the T1 is at higher temperature than T2. So our dt here is something like T2 minus T1. So this has a lower temperature than this T1. So let's group like terms. So we can say Q dr is equal to negative 2 pi KRL dt. You can divide through by R. And then we are going to get Q dr over R is equal to negative 2 pi KL dt. So we can integrate, right, from R1 to R2 because there are two radii and this is a smaller one, this is the bigger one. And then here too we can integrate from an initial temperature to the final temperature. Now the initial temperature is rather the hotter one and then the final temperature is the colder one. So T1 to T2. When we differentiate this with respect to R, we are going to get Q ln R. So from R1 to R2. And this will also be negative 2 pi KL T from T1 to T2. So we are going to get Q ln R2 minus ln R1. And this is equal to negative 2 pi KL T2 minus T1. So we get Q ln R2 over R1, and this is equal to minus 2 pi K L to T2 minus T1. Now the negative, if T2 is at a colder temperature and T1 is at a higher temperature, so when we rewrite it well, we are going to get 2 pi KL T1 minus T2, right? Because you are negating through. This is at a lower temperature, this is at a higher temperature. And it's supposed to be the higher temperature and the colder one. And then our KL becomes 2 pi KL T1 minus T2 all over ln R2 over R1. So now it means that for heat of conduction through a pipe, the heat, this becomes the equation for the heat transfer. Now already we said that you can write heat transfer to be in the form of K is equal to change in temperature over R. So now from this, our R will just be, so 1 over R will be equal to the whole of this, right? Equals 2 pi KL all over ln R2 over R1. So we are going to get R being equal to ln R2 over R1 all over 2 pi KL. So now this becomes our resistance conduction through a cylindrical pipe. Now, so let's say there is a convection too, right? So with that same pipe, we have a fluid flowing through, right? So we have a fluid flowing through. So this is our cylindrical pipe, right? And then, so our pipe has inner radius and outer radius. So let's say there is a hot fluid which has heat of convection. For the moment we say a fluid is flowing through the inner pipe, then it means that heat will be transferred from the hot fluid to the surface of the inner pipe, and that is by convection. So the heat of convection of the fluid should be there, and also the temperature of the hot fluid should also be there. Right? So if this is our center, here is R1 and here is our R2. The heat transfer will be in the radial direction. So now for convection, we are looking at from the inner, from the fluid to the outer, to the inner of the pipe, right? So our heat of convection will just be HA THF minus T1. We are calling the temperature here to be T1. And then because you're looking at cylindrical pipe, our A is 2 pi RL. So K of convection becomes H2 pi RL multiplying THF minus T1. Now this heat of convection from the hot to the inner of the pipe should be the same as the heat from the inner of the pipe to the outer, right? And that was by conduction. Right? We can say heat of convection is equal to heat of conduction. And then we can have something like 2 pi RL each THF minus T1 should be equal to, so this is our Q, right? And then this also works. So that same Q is 2 pi KL T1 minus T2 all over ln R2 over R1 equals Q. So this equation 1, this is equation 2. So we can compare them. So we can say that 2 pi r l h t h f minus t1, right? When you make this in the subject, so when you are making, just like how you did for the composite walls, so when you are making THF minus T1 the subject, you are going to get Q over 2 pi RLH. And then when you make T1 minus T2 the subject, you are going to get Q ln R2 over R1 all over 2 pi KL, right? So now we can add the two equations. When we are saying this is equation 3 and this is equation 4. So equation 3 plus equation 4 is going to give us THF minus T1 plus T1 minus T2 should be equal to, so you are going to add this and this. You can factorize Q over 2 pi L out. And then you are going to get 1 over, for here you are going to get 1 over H, right? 1 over HR, so 1 over RH plus, here you are going to get ln R2 over R1 all over K. I think I should extend this. So we have, so now T negative T1 and then this T1 will cancel out and we are left with THF minus T2 should be equal to Q over 2 pi L multiplying R. So this is supposed to be R1, right? This is supposed to be R1. So let's choose where this 2 pi RLH comes from. So it comes from here, right? And then the area will be radius 1 because it's by convection. The convection is from this fluid in the inner radius of the pipe. So here is R1, right? And then our H here becomes the H of the hot fluid. So we should just put it there. So here is H of the hot fluid. But that's what we are considering. The hot fluid inside the pipe. So 1 over HHF R1 plus. So now here we have the ln R2 over R1 all over K. Right. So that's what we have here. So here was 2 pi KL and then we factorize 2 pi L out. So you are left with K. Yes. So that's it. So now what's the way forward? We have THF and then T2. So just like the composite one, realize that if you are considering just one pipe, it's going to be T overall, and then T overall is the inner to the outer, right? So this that is given as the T overall. So we can make our Q the subject here and see that our heat transfer will be 2 pi L THF minus T2 all over 1 over HHF R1 plus, so it's going to be ln R2 over R1 over K. Yes, so this will be our heat transfer. Now, when you look at the heat of um, conduction that we did for the cylindrical, so looking at this, we can see that our Q heat transfer is equal to 2 pi L. So now our 2 pi L wouldn't change no matter the number of pipes you are looking at. If you are just looking at one pipe and then the fluid is flowing through. multiply THF minus T2 all over 1 over HHF R1 plus length R2 over R1 all over K. So now this becomes our final equation. Now this equation wouldn't really change depending on the number of pipes. The only thing that is going to change will be our T overall, because now this is going to be our change in T overall. So now when you are considering about 5 or let's say 3 pipes fused together, right? So this is the center of the pipe. We have one pipe. We should also take note when you say a pipe is not just something thin. It has a thickness, right? And that's giving us the outer radius. So this hole is just one pipe. So we can see this is pipe A and this is pipe B. Now pipe A is fitted into pipe B. Pipe A is fitted into pipe B, right? And then a hot fluid is made to flow through. When the fluid is flowing through, it's going to recede to the inner wall of pipe A, and then that will be by convection, and that's this portion of it. Right? And then when the inner portion of pipe A gets heated, it's also going to recede to the outer of the same pipe A, and that is ruled by conduction, and that's for this portion. Since we did up to this portion, now when you have an extra pipe, then it's going to lose heat to, if you are considering this is R1. From here, sorry, from here to here is R1. From here to here is R2. And then from here to here is R3. And then we ended up to R2. So that's why you have this one here. Now let's say we have an additional pipe, which is pipe B fitted inside. Then at this point, outer surface of the A is going to lose heat to the outer surface of pipe B, right? Because the inner of pipe B becomes the whole of this. So the outer of pipe B will also be by conduction. And now also we can derive it based on this. So we just learn R3 over R1 all over the K of pipe B. So now this becomes K of pipe B. Now when you have the cold fluid here, that means the pipe B, the outer of pipe B is also going to lose heat to the cold fluid here. And that will be by convection, right? You are just going to repeat the same as this. So plus 1 over HCF. So this will be for the cold fluid. And what will be the radius? It will take the radius of pipe B, right? R3. So that becomes the general formula. And then in this case, our change in T overall wouldn't be THF minus T2. It's rather going to be THF. It's rather going to be THF minus the T of the cold fluid. So T of the cold fluid. Now let me clean it and write the general. So now the general equation becomes Q is equal to 2 pi L. The 2 pi L here wouldn't change, right? Multiplying change in T overall all over summation of resistance. And then the resistance here is, if it is for conduction, then R2 over R1 all over K. If there is another conduction, then R3 over R2 all over K. And then if there is convection, 1 over HR. So you just need the heat of convection of the fluid and then the radius of it. So that will be all.